So, welcome to the new lecture of the course, Properties of Materials. So, let us just briefly recap what we did in the last lecture. So, in the last lecture we talked about strengthening mechanisms. And we were mainly talking about precipitation strengthening. Which is a very common mode of strengthening in aluminum copper alloys and variety of other alloys, and depending upon the particles, depending upon the size of the precipitates and their distribution, you may have either shearing of precipitates or the precipitates can help in Porovon strengthening by creating resistance to dislocation motion. So, this will complete the mechanical behavior part. So, in total we have discussed 4 strengthening mechanisms. The first one that we discussed was you can say strain hardening, where you deform the material and it gets harder. Second one is grain boundary hardening, where strength is increased by deforming by reducing the grain size of the material. By the way, all of these mechanisms are valid especially for metals, they may not be valid for ceramics. And then we looked at solid solution strengthening, and finally we looked at the precipitation strengthening or hardening, which is especially true for age hardenable alloys. So, this completes our discourse on mechanical properties of materials in general. Now, let's now move on to the next topic, which is on electrical properties of materials. And electrical properties of materials are basically those properties which are determined by. So, one of the parameters which actually defines the electrical properties of material is called as electrical conductivity. Okay. Electrical conductivity, which is represented as sigma, or you can say its electrical resistivity, which is represented by rho, and the sigma happens to be 1 over rho. So, basically what this does is it defines the ability of a material to conduct electricity. So, electrical conductivity is about ability of a material to, you can say, conduct charges. Just like heat conduction, it is electrical conduction. So, there are a variety of electrical properties of materials that are there. So, you have electrical conductivity, you have resistivity, you have dielectric constant, and magnetic properties are there. So, we are not going to talk all of them, we are just going to restrict ourselves to the conductivity or resistivity here. So, based on the magnitude of this electrical conductivity or resistivity, we define materials as one which are highly electrically conducting. Such materials are generally called as conductors, and examples are typically metals. Metals are very good conductors of electricity. Okay. And then you have another category, another extreme, which is poorly electrically conducting, which is basically a insulator. So, such materials are basically insulators, and examples are oxides and various other ceramic materials are insulators. And there is an intermediate category which is called as semiconductors, which are neither completely very highly metallic and or insulating, and examples of these could be silicon, germanium, gallium arsenide. Some of these materials are semiconductors. So how do you define the values of these to distinguish them? So for metals, the range of sigma, so if I look at the range of sigma in ohm centimeter in ohm meter inverse, let us say, then for metals this is about generally greater than 10 to the power 5, whereas for semiconductors it is between 10 to the power 5 to 10 to the power minus 6, and for insulators it is generally less than 10 to the power minus 6 ohm meter inverse. Okay. And so if you look at copper, for example, which is a very nice electrical conductor, for copper this value is 5 into 10 to the power 7 approximately plus 7 ohm meter inverse. And if you look at the same value for semiconductor like silicon, for silicon this value happens to be of the order of 10 to the minus 4. And if you look at for something like quartz, which is an insulator, this value is 10 to the minus 18. And if you look at something for a typical polymer, for a polymer this value is approximately 10 to the minus 14. So these are the sort of differences in the magnitude in terms of basic electrical property of a material, which is basically electrical conductivity or resistivity. So this is the conductivity value. So you can see that rho will be, so if you want to now determine rho would be nothing but 1 over 5 into 10 to the power 7. For this it would be 1 divided by 10 to the power minus 4. For this it would be 1 divided by 10 to the power minus 18 and 1 divided by 10 to the power minus 14. So for metals electrical conductivity is high or resistivity is low. For insulators it's converse is true, which means the electrical conductivity is lower and resistivity is very high, and semiconductor fall in between. Now to understand the electrical properties, the basic law that we use is called as Ohm's law. Okay. And Ohm's law is, we have all studied in our schools. So if you have a bar of length L of cross sectional area A, okay, so let us say this is the bar of length L and the cross sectional area is A, and if it is attached to a bias, let us say voltage applied is V, then assuming that only one type of carrier moves, we may have multiple types of carriers in materials, as we will see, only one type of carrier moves, then we can write, so which has, let us say for this carrier it has a charge Q, it has a number density, which means number of carriers per unit volume, let us say small n, and it has a mean velocity which is or one can also say this is called as drift velocity, which is equal to V, and this is along the axis in this direction, so unidirectional. So from this one can calculate what the current density is. Current density is defined as J, which is current divided by area. Okay. So what is current? So we know that Q is equal to IT. So I becomes equal to, let us say, capital Q divided by T. So number of charges flowing per unit time. So if you now do the math, so this will be number of charges per unit volume. Okay. And this is number of charges per unit volume, and this is the velocity. Velocity is nothing but meter per second. So if you do the math here, so total amount of charge basically per unit volume will be N into Q. So the current density in that case would be N into Q into V, N into Q into V. So if you look at this, this is number per meter cube, this is coulomb, and this is meter per second. So this will become meter square. So what we get here is number of charges per unit time per unit area, and that is what we said I was equal to total amount of charge flowing per unit time per unit area will make it current density. So, assuming that electric field is uniform throughout the solid, so if electric field is uniform, then we can write this E as voltage divided by the length, and for most conducting materials, if we say that this velocity is proportional to electric field, if this relationship is true, and then we write this V is equal to mu into E, where mu is a constant which is called as carrier mobility. So, I was going to write something else, but we will invoke that little later. So, this is called as electrical carrier mobility. Okay. So, V is equal to mu E, then I can write this J as NQ into mu into E, and this is basically what is called as basic forms of Ohm's law. So, you can see that J is equal to NQ mu into E. Okay. So, we can write this as J is equal to sigma E, where sigma is NQ mu, which is basically electrical conductivity. You can also write it a little differently. So, if you write this E as V over L, then I can write the value of V, which will be equal to 1 over NQ mu into L divided by A into I, because J is I divided by A, right. So, I can manipulate this equation in this form, and we know that another form Ohm's law is V is equal to IR. So, this term is basically R term, and this here is, you can say, electrical resistivity rho, which is 1 over sigma. So, R you see here is rho L divided by A. Okay. So, you can see that here, if you take R is something which dependent upon L and A, which is the length and area, whereas N is a term which whereas rho is a term which depends upon number of electrons per unit volume, the charge of carrier, number of carriers if not electrons, and the mobility. All of these are constant for a given material, okay, or made by. So, this is basically, you can say, material property where R is dimension dependent. So, it is not the resistance which is material's property, it is actually the resistivity or conductivity which is the intrinsic property of a material, which can be changed by changing its processing condition, changing its microstructure, changing grain size, and so on and so forth, as we will see later on. But for a given material, rho is constant, but R can be changed by changing the dimension. So, if you increase the length, the resistance will increase by 2 times. If you decrease the cross sectional area by 2 times, the resistance will decrease by 2 times, but the rho will remain constant for the same material. Okay. Now, the question is, we said carrier, okay, what kind of carrier? So, let us bring ourselves to nature of carrier. Okay. There are 2 kinds of, so in crystalline solids, there are 2 kinds of, so in solids there are 2 types of carriers. we can talk about one is the electronic charge carrier, which in case of metals is electron and ion itself. The ion itself, ion can also move. So this electronic charge carrier is basically it's a point charge with very little mass. Okay, so it carries a charge. So Q for this is E. Okay, so you can say E and M is equal to M E. These are the fundamental quantities, and this Q is 1.6 into 10 minus 19 coulomb, and this is 9.1 into 10 minus 31 kg. Whereas for ions, ion depends upon, ions are nothing but atoms with charges gained or lost. So basically these are ionized atoms, so with plus or minus electrons depending upon is a cation or anion. It has a mass which is significantly higher than that of an electron. So basically it has approximately mass of an atom approximately, and then it is much heavier than electrons, and the radius of, so for a point charge you cannot define a radius, but for ions the radius varies anywhere from 0.05 to 0.25 nanometer, ballpark figure. Okay, so as a result you can see because of its larger size and heavier mass, electrons are far more mobile as compared to, so electrons so that is why most materials, in case of most materials we talk about electronic conductivity. There is something called as ionic conductivity as well, which is important in the context of ionic materials, especially in ionically conducting solids, but we will not invoke here. So for most materials what we are interested is in electronic conductivity. So the conductivity that we saw earlier, sigma was equal to Ne mu. This is basically electronic conductivity here, sorry, NQ mu. So Q was basically electronic charge, mu you can say is electronic mobility, and N would be number of electrons per unit volume. So these are basically the considerations of these. So basically electron is the dominant mobile species in electrical conduction in most material, especially in case of metals and semiconductors. If you look at metals, in case of metals we generally talk about electrons which are mobile are the electrons, not the bound electrons. So basically carriers that can take part in conduction are not the bound electrons, but the what we call as valence electrons, which we call them as free electrons. And valence electron generally they are smaller in number. So although theoretically you can have up to 10, 12 of valence electrons, but generally the valence electron number varies from 1 to 2 to 3, something like that. So for example, for copper Copper is 29, right? So we can write for copper it's 1s2, 2s2, 2p6, 3s2, 3p6 and 3d10 and 4s2, 4s1, okay. So generally for copper this is one electron that is available for conduction, one valence electron. You can write this as Ar 3d10 4s1 as well because this argon will complete its shell up to this point, okay. So that will make it 18. So 18 plus 11 will make it 29. If you look at manganese, manganese will give you 1s, so manganese will give you argon into 3d5 4s2. So potentially speaking, manganese can have up to 7 valence electrons, but generally the valence states which are available for manganese are 2, 3 and 5, okay, 2, 3, 4, 5. These are the valence states which are more common for manganese, but it can have up to 7 valence electron. So generally speaking, valence electrons are 1, 2, 3 are the typical number of valence electrons, and these are the basically outermost electrons which are detached from the atom. As a result, these electrons make, so these loosely bound electrons form what we call as electron gas or electron cloud, and these are also called as free electrons. So if we look at the, so now having said this, so you have these free electrons which take parts in conduction in materials. Let's now look at the classical theory of conduction in metals, which is based on these free electrons or valence electrons. So if we look at the classical theory of conduction in metals, it was developed by two people. One is Drude and second is Lorentz in 1905, okay, who assumed that, so what are the assumptions? These were the guys who basically established the basic framework of electronic conductivity of metals. So first is that electrons are the charge carriers. Secondly, electron cloud acts like a ideal gas in which electrons are non-interacting, okay, and then these electrons under the application of electric field they move, and when they move they collide with either lattice atoms or fellow electrons when in motion, okay. So when they undergo collision with these lattice atoms and electrons, we define a time which is called as average which is defined as tau, and this tau is called as a relaxation time, and this tau is the one which makes up this term. So, we saw that J was equal to NeV, okay, and which was equal to Ne mu into E. So, we said that sigma was equal to Ne mu, but we did not define mu what it was. So, mu is equal to mobility, which is equal to E tau divided by m. So, you can write now this as Ne square tau divided by me. You can say this is me. So, we have replaced q by E and mass of electron is me. This is what the sigma value is now in terms of number of electrons and E square tau divided by m. So, when the problem, so this says that n is, so here you can see that E is the electronic charge, tau is the relaxation time, the time is spent between two successive collisions, m is the mass of electron. This n is basically, you can say, is the number of conduction electrons. So, the question is, how many electrons do conduct? Is it all the electrons which are conducting? Do all of them have similar energy, all of them are conducting? Or is it only a certain number of electrons which conduct and give rise to? The answers are not very obvious from resistivity calculations. Another problem that occurs is with this model is, so first of all, we are not able to conclude from this that how many are the number of electrons which are conducting. Is it all the conduction electrons which are conducting, or is it only a certain set of electrons which are conducting? It is not possible to tell the obvious answer from resistivity. However, there are other clues which tell us more clearly with respect to some problems. So, the problems which arise are: number 1, if you assume that, now you are assuming that this free electron cloud acts like a perfect gas, okay. If it acts like a perfect gas, then we can assume that kinetic energy of a free electron will be half MeV square, right? And if it acts like a perfect gas, then this will be equal to 3 by 2 kBT, right? Assuming, so which means that V should be proportional to T to the power 1 by 2, that is what it follows from here, okay. Which means, now we saw that J was equal to NeV, right, which means this current density should, which means that J should also be proportional to T to the power half. If J is proportional to T to the power half, then even 1 over sigma or rho should also be proportional to T to the power half, right, because J is equal to sigma E, right. So, which means 1 over sigma, that is rho, that should also be proportional to T to the power half. Now, this is what this model says, but experimental observations suggest that rho is a function of t, linear function of t. So, when you plot, for instance, this rho versus t, the ruled theory says that my variation should be like this, rho should vary as T to the power half, but experimental observations say that this is a relation, it is proportional to t. So, let us say this is b T to the power half, this is a t, something like that, okay. There is, however, a point at which both of these are similar, or they are in the vicinity of each other. So, if you are measuring at this temperature, which is, let us say, Ts, then you would not find a difference. So, unless you make a temperature dependent plot of resistivity, you will not be able to find out whether the model is correct or not. It is only when you make this temperature dependent plot, you say that the model predicts a behavior of T to the power half, but the experimental observation give you a behavior which is which says that rho is proportional to T. So, this is the first problem that we encounter with Druth's model of, mainly that all the electrons are non-interacting, they behave like a perfect gas, they have energy which is half mv square, and all of them have same energy 3 by 2 kT, right. So which means when temperature goes to 0, the energy also goes to 0. If energy goes to 0, the specific heat also goes to 0. Another problem arises is the specific heat. So the problem number 2 is, let us say if mean kinetic energy of a free electron, as we saw, was equal to 3 by 2 kBT, that means the heat capacity will be, and if we say per mole, then you just have to multiply this by Avogadro number. This will become 3 by 2 kB into Na, which will be equal to 3 by 2 R. All right. Assuming that we have 1 electron per atom. So 1 electron per atom is the assumption. So of course, if you increase the number of electrons, this will increase. So heat capacity per mole, each atom has 1 electron, which means it will have 3 by 2 kB into Na, which will be equal to 3 by 2 multiplied by R. Now lattice heat capacity, on the other hand, if you go from the thermal properties, lattice heat capacity turns out to be 3R. So which means for a monovalent metal, the heat capacity, the molar heat capacity will be equal to 3R plus 3 by 2R, which will be equal to 9 by 2R. Okay. Experimental values, however, are approximately equal to 3R. So does it mean that electrons do not contribute to heat capacity at all? Okay. Now if that is the case, then it is not consistent with the ideal electron gas model. So the question arises whether electrons don't contribute to heat capacity. That's the question. So these are the two disagreements that we see when we apply this ideal gas model of free electrons. And of course there are other issues like whether all the electrons should be contributing to conduction and things like that. And these answers are solved to some extent by considering what we say is quantum mechanics. So to answer these ambiguities, or let us say issues, or to resolve, let us say not answer, but to resolve, we take help of what we call as quantum mechanics. So basically what we have done is we have looked at the classical behavior of electrons, where we say that conduction in metals takes place by the means of conduction of free electrons, and they follow this relation J is equal to sigma E, where sigma is the electrical conductivity, which is given as Ne square tau divided by M, or Ne mu, where mu is the electronic mobility and tau is the relaxation time. But there are questions with regard to consideration of this free electron gas model in terms of, one, rho is proportional to T or rho is proportional to T to the power half. The classical gas model says this, whereas reality is this. Similarly, classical gas model says that my specific heat should be 9 by 2R, but experiment says that it should be equal to approximately 3R. So there is some problem in terms of number of electrons perhaps contributing to the total cause here, and this is what is going to be resolved by the use of quantum mechanics that we will take up in the next lecture. Thank you.